Welcome back to Lecture 2, the manufacturing process. And beforehand, we talked about a process primer, just an introduction to the CMOS process. Now we'll go into a detailed description of the CMOS process flow. Okay, so we have down here our advancement, our progression in the lecture. And as we showed before, we're going to start with the silicon wafer. Well, the silicon wafer is started with the Czochralski process, and that's a process where we take this very good and clean seed of silicon, like a long wire of silicon, and similar to the way you make rock candy, we're going to stick it into this vat, which is going to be hot with gas, silicon gas around, and we're going to turn it around, constantly turn it around and pull it up, and little by little it's going to come out with this piece of very clean intrinsic silicon, and it's so clean that we have the so-called 11 nines, 99.999999999% purity. What that means is it's the maximum purity of starting a silicon wafer is equivalent to 1 milligram of sugar dissolved in an Olympic-sized swimming pool. So that's really clean. The P-type that we've discussed before, that's something that we dope it purposely afterwards. After we pull this out, we get what we call an ingot. Okay. And the ingot is this really long tube, which is at the diameter of our wafer that we want. Wafers are usually 30 centimeters in diameter nowadays for the big wafers, a 12-inch wafer. Here you can see one that's a 15-inch, 450 millimeters, like a basketball hoop, and the ingot is also the height of a basketball hoop, pretty much. Then we take this thing and we slice it, and you get these wafers that you can see here. Now, if you look at the wafers, you can also see that there's an edge, a straight edge, and that's to tell the wafer orientation when we stick it inside the different machines. Okay, so we had our silicon wafer, and now we said that we need to build this field oxide, this FOX, which is going to separate between the areas of the active, the transistor areas, to differentiate between them. And we're going to start with the old way of doing it, which was called the LOCOS, or local oxidation process. Okay, so we start with our wafer and we grow a little piece of silicon dioxide. This is not the gate oxide. It doesn't have to be that accurate, but it's going to be a seed for growing this LOCOS. And we cover it with this nitride, this silicon nitride stuff. Okay, then we're going to dump our photoresist. Remember I showed you before photoresist, the purple stuff? Well, it really is purple. And you see here that we spin around the wafer and dump this plastic stuff in the middle, and it spreads out equally onto the whole wafer. Okay, so we have this photoresist covering the wafer, and then what we're going to do is we're going to bring our photo mask, which is going to have our different features. In this case, it's just a square in the middle, and it's going to harden the photoresist over here. Okay, and then we're going to wash off our photoresist and etch away the nitride that was there. So what we have left here is we have a piece of nitride, and where our active area is going to be, where we don't want to grow our LOCOS, where we don't want to grow our field oxide, and on the two sides we have a seed of silicon. Okay. Doing that, we can now put this in an oven that's going to have the silicon grow based on the seed here, but it's not going to grow where we have this nitride protecting it. So we'll clean away the photoresist and let the field oxide grow, and it's going to grow both up and down and make us a nice big field oxide that's going to differentiate our active area. However, when we do this, it doesn't come out that great. By the way, we can etch away our nitride and our little piece of silicon afterwards. As you see, what happens is this seed that was over here, the nitride, it protects what's underneath it, but it still grows into the sides. Okay, and then when we look at it, what we get here is we get it's not that nice and beautiful and straight. It actually has this little point over here, and we call this point a bird's beak. Somebody decided it looks like a bird's beak, and that's a problem because it makes the minimum separation between two field oxides larger than something small, and when we make the transistors smaller and smaller, we want to be able to do this more accurately. Okay, that leads us to the STI process, but there's actually another problem that we didn't discuss before. So one is this bird's beak, which makes it hard to make the transistors close to each other. And the other problem is that we have a parasitic MOSFET that can turn on underneath the field oxide. So look at this. This is silicon dioxide, right? And this is a P substrate, okay? So if we put, say, metal 1 on top of this, what we get is a MOS. We get a MOSFET. And in fact, we can have some currents that are running through this MOSFET if we turn it on. Now, how would we turn it on? By putting some sort of voltage here, it could cause a channel over here. And we don't want that to happen. So let's see how we fix that while we also fix this bird's beak problem. The way we're going to do it is with field implants and the STI, the shallow trench isolation process. Okay, so we start as before. We have our active areas over here. They're covered with nitride and the photoresist over here. Okay, and now what we're going to do is we are going to etch away the nitride. We're going to etch away the silicon that was before. The photoresist is protecting us from the etch, because the etch is like some bombardment of some material that's eating away the stuff that was above. And we keep on etching until we trench a hole into the substrate. So that's why it's called shallow trench isolation, because we actually dug into the silicon this time. Now, before we do anything else, we are going to implant some p-type. Okay, so this is p-type implant. And what is this p-type implant? It basically means that now once we have a field oxide over here, the parasitic transistor that we're going to make, it's going to have its M, O, and S, but we have a lot of P's in here. And that means that to cause inversion here, we'll need a much higher voltage than we're going to actually put on the metal, and it makes this transistor going to be really hard to turn on. So that's our field implant. Okay, hope you understood that. And after we implanted with our p-type over there to ensure that we don't have this parasitic transistor, or that the parasitic transistor has a very high threshold voltage, what we're going to do is we're going to grow an oxide from the bottom of the trench up. And when we grow the oxide like that, it doesn't actually cause any bird's beak. It just grows anisotropically straight up. So we got our nice shallow trench isolation, and then we can do this really close together, plus we eliminated our field oxide, our parasitic transistors. Okay, that leads us to the next part, which is well implantation. So how are we going to make our wells? We're going to cover our wafer with a thin layer of oxide, and then implant the wells through the photolithographic process. Pretty straightforward after what we've done before. But one thing that happens is that after we bombard our wafer with ions that are going to get stuck inside for the doping, right? What's going to happen is it's going to break our beautiful crystal that we started with after building our ingot, right? So we had this great crystal, and then we're going to do these implants. We're going to shoot atoms at the silicon, and it's going to go in. They're going to go inside, and they're going to break up our nice crystal. So what we have to do is we have to do something that we call annealing. Okay, so annealing is basically heating up the wafer to fix the covalent bonds, and we have to do this after every ion implantation or any similar damaging step. And what it does is it gives the atoms inside the crystal a lot of energy, and once they have energy, they can move, and they move to their lowest energy point as we cool it, and their lowest energy point is their nice crystal structure. So that's annealing. There is a side effect or a drawback, which is diffusion. Once we gave these atoms heat, they're going to diffuse, they're going to move around, and then we may not get the pretty feature that we made. So if we tried to make a well that looked like this, after diffusion, it's probably going to look something like this, because of diffusion, the atoms are going to move all over the place. Okay, so that's something that we have to know. There are lots of ways to do annealing. Annealing can be problematic because, again, we have to heat up the wafer, and it can cause different layers that we've made to melt or to be ruined. So we have to be really careful when we do it and know where we're doing it along the way. So there's something that we didn't discuss in a basic circuit course, and that's the question is if we can change the body voltage of an NMOS transistor. So before we saw that if we had a PMOS transistor, it was no problem, right? We had our substrate, we put an N well inside the substrate, and then we had our PMOS transistor over here. And what we did is we put an N plus type of diffusion, and then we could have put any voltage we wanted over here. We couldn't do the same thing with the NMOSs because the NMOSs are inside the substrate, which is grounded. And if we change the body voltage here, if we put some sort of VB, it's going to happen to all of the transistors and not only the ones that are isolated inside the N well like here. But can we, but what if we still want to change the body voltage of an NMOS transistor? And we can. We use a triple well process. Okay, so it does cost a lot of area, but it is very doable. So on the left here, we have just a standard N well. We're going to make our PMOS transistors, right? And on the right here, we just have our standard P well where we're going to make our NMOS transistors. But this is connected to this, and this is connected to ground, remember. So all these NMOSs, their body is at ground. Again, the PMOSs, their body is at wherever we connect the PMOS, wherever we connect the N-well, which is usually going to be to VDD, but it can be to some sort of bias voltage. But if we want to make an NMOS and connect it to something other than ground, we can do this. We can make a swimming pool here, which we call a deep N-well. So we put a N-type material really deep inside the substrate, and then we fill that with a P-well. Okay, and that's an isolated P-well because on all sides it's going to be covered with an N-type doping, and we have to again make sure that we have our diodes in the right directions here. So this is an N-well, and we get this diode that's over here. Remember, this is at ground, so and also we get another diode that's over here, right? And what we know is that this is going to be higher than ground. So what we have to do here is connect this to VDD in order to make sure that these NMOSs will never turn on and everything is fine. Okay, so how are we going to do that in our layout? Well, we're going to start with an NMOS transistor here. It's a poly over diffusion, and we also have a contact, which is this contact. We have a contact over here that's going to be our contact to VB, whatever it will be. Okay, so that's our contact over there. And now, what are we going to do with it? Okay, first of all, we're going to put a deep N-well layer. So that's going to make this part of the process. That has to be, again, this is only a cross section, but when we take it from a bird's eye view, which is how we do layout, we're going to have to put that all around. So this is the bottom of the swimming pool. Okay, and it's going to have some pretty big margins on the side. Okay, but we now need to make the side walls. Okay, so how are we going to make the side walls? With a standard N-well. As you see, it's the same type of a layer like over here. So we're going to put a standard N-well on the 4 sides and make sure it's closed. Okay, now what's our last thing we have to do? As we said before, we have to make sure that this thing is connected to VDD. So we put our N plus contacts and we connect it to VDD. That's this guy over here. Okay, so now we're going to have this deep N-well around. That's the light blue layer. The N-well is the darker blue layer, and the masking tool will understand that it has to put an isolated P-well in the middle. Moving on from the well implants, we're to the point where we're doing transistor fabrication, and this is probably the most important, complex, and so forth part of the process. I'm going to discuss a few points in transistor fabrication. The first one is the VT implant. So the threshold voltage of a transistor, as we remember from previous courses, is the flat band voltage, the Fermi voltage, etc. And there's this factor here, Q implant divided by Cox, which is basically the charge that is implanted into the transistor. We call that the VT implant. So we can implant this QI, this implant charge, and that will help us set the threshold voltage of the transistor. Okay, we can use a lot of implant to change us to a high VT transistor, to a low VT transistor, and so forth. There's one thing that's called random doping fluctuations, which is a distribution of the VT between devices. It causes the fact that 2 devices that are next to each other do not come out exactly with the same threshold voltage, even though they were supposed to. We'll discuss that a bit more later on. And there's another point where we can also implant the transistor in such a way that we bring the threshold voltage to about 0. These are called native transistors. You may see them in different process design kits. It's similar to what used to be called a depletion transistor, which means it's an always-on transistor. To turn it off, you have to use a negative VT, but it's mainly used in analog type circuits where you want to remove the VT drop over an NMOS. They are not a standard transistor, and therefore they require larger DRCs. You need to have bigger spacing and so forth around them, but they do exist in many design kits. So ion implantation, as we said, is the way that we accelerate ions to get them down and into the silicon itself. So here's just a picture of it that you can see. That's kind of nice how the ions are shooting down into the wafer. Depending on their speed and the magnitude of the strength of the ion beam and the flux, we get a certain amount of ions at a certain depth inside our wafer, and that's how we basically dope and so forth. Okay, the next part of transistor fabrication is the gate oxide. And gate oxide thickness, Tox, is one of the most important device parameters. As I told you before, as I mentioned before, being able to build to grow a gate oxide, a good gate oxide, was one of the things that kept the MOS technology on the shelf for many decades, until finally towards the end of the 70s and the early 80s, they got it to be a good enough and clean enough process that we could build a good gate oxide. And now it's very well under control. It's gotten to the point where scaling the gate oxide has gotten so small that at 45 nanometers, the gate oxide was 1.2 nanometers thick, as you can see here. Now 1.2 nanometers is very, very small. That's about 5 atoms. You can pretty much see them here in the picture. Okay, that's really small. We'll see that causes problems, that there's actually quite a bit of tunneling that comes from the gate down to the substrate or the channel underneath, because it's such a thin layer. Okay, it has to be done under super clean conditions to eliminate traps and defects, but that's actually, as I said, done really well. And nowadays we often use high K materials, which are different materials. They're not silicon dioxide, and this complicates the process a lot. Just an interesting anecdote here. One of the reasons that silicon is actually the material of choice, and it's the substrate that we use and so forth, is because MOSFETs, we were able to build them by actually oxidizing silicon, and we got silicon dioxide. And this is a very nice type of a chemical reaction where we can get a good interface where the gate oxide connects really well to the silicon substrate, and we can grow it very clean and so forth. So that's one of the reasons the silicon went out. I mean, there are other reasons, for example, that it's sand and we can find it all over the place and it's cheap and easy to use. But to make MOSFETs, this interface between the silicon and the silicon dioxide was very important. And changing our materials several years ago to high K materials, where it is not silicon dioxide, it's other things that based on hafnium and so forth, is actually going and taking our basic assumption where we have this good interface between the silicon and the silicon dioxide, throwing it away and starting over. But that's what is done now. The next stage I wanted to talk about was the gate etch. So originally aluminum was used for the gate material. That's why we got our MOS, right? Metal oxide semiconductor. Then polysilicon was used. The reason that polysilicon was used is because it had a better work function. It was easier material to work with in that way. But now, after changing over to high K materials, we've gone back to metal gates. Okay, the gate is the smallest dimension that's fabricated through photolithography. So again, we have this gate that is supposed to be a piece of polysilicon or of metal nowadays, a very, very, very small piece of oxide, and then we have our substrate, and our substrate is supposed to have these wells on the side. So the way we do it is by self-alignment, as I mentioned before. We start with our substrate over here. We grow our very thin gate oxide that we saw before as few nanometers thick. Then we grow our polysilicon onto it, or depose our polysilicon or our metal gate. Finally, we with photolithography, we make our gate size. Remember, this is the smallest dimension that we're going to be fabricating. So this is our L minimum. This is our 7 nanometers or 5 nanometers that we make today. Then we're going to etch very anisotropically. So we're going to etch directly down, and it's going to cut both the polysilicon and the gate, and it's going to be completely aligned, so we don't have to have some complicated alignment between it with very little mistake. Okay, so that brings me to talk a bit more about photolithography. So what is photolithography? It's from Greek, so photo means light, lithos means stone, and graph means picture. So literally this means carving pictures in stone using light. Okay. So photolithography is taking this mask, photo mask, that's this quartz glass type of thing, and covering it with chrome. So here on the bottom you see this opaque material is chrome, and then carving holes in the chrome basically. Photoresist is the organic material that we have on the bottom here, the purple thing in my pictures before, and it's sensitive to light. So for example, when the light comes through, it will harden these areas, and then we can wash away the parts that aren't hardened, and we just are left with these pieces of hardened material. It can also be the opposite, so maybe where everything gets hardened except for the places that we filled, and then we'll wash away just them. Anyway, after doing that, we can do all kinds of things to our substrate that's covered now with the photoresist. So the interesting thing is the resolution of the light. So for photolithography, obviously we need to decide what the resolution is, what's the size of the dimensions that we can make, how far away from each other they can be, and so forth. And there's this well-known equation, K1 times lambda over n sine alpha. So this d over here is the minimum pitch, the dimension. Lambda is the wavelength, and we'll discuss in a minute that the wavelength of the laser that we use for the last 20 years or maybe even more is 193 nanometers. And remember, we're making transistors nowadays 7 nanometers. 193 nanometers is quite big. Then we have the refractive index, n, and we usually take 1 for n because the refractive index of air is 1. And we have alpha, which is the angle of acceptance. The bigger the angle here, the larger the lens. So this thing together, n sine A, is called the numerical aperture. And we have K1, which is a material constant, which is about 0.8. Okay, so looking at that, how are we supposed to get smaller and smaller indexes? So this, remember, is 193 nanometers. We need to take 193 nanometers and make dimensions that are really small. It's commonly known with this equation that we can pretty much print things that are a quarter of the wavelength, so about 50 nanometers. That's what was known, and that's what was actually thought to eventually stop Moore's law. However, we've played a lot of tricks along the way, and we're not actually limited by photolithography currently. So one of the ways to do it is, again, we're going to take all of these things and try to improve them, is to change this n, right? We want to make this n larger. So if we, instead of using air here, so this is one of these focal lenses. It's a big lens, and it would be shining its light through here onto the reticle, onto the wafer. Instead of using this, instead of keeping air here in the gap, you can put a different substance, for example, a droplet of water, and water has a higher refractive index. So that is called wet lithography or immersion lithography, and it's commonly used nowadays. Okay, there are many mask and layout techniques. For example, if you look here, this is a microscopic image of SRAM, and you can see that everything is very regular. You see that all of these lines are exactly the same space away from each other. They're all very straight. They're the same orientation. In fact, this is something called double etching. So what we do is we use the optical features of making these things. We can tune it to make to cover the whole wafer basically with these straight lines, and then we can on a separate process step we can go and just etch away the areas we want to break it, and this is a much higher resolution. Much lower resolution, so it's a much larger distance and it's easier to etch these things away. So that's called a double etch, because we first etched away this stuff in the middle and then we etched away these parts over here. Okay, obviously we can use a smaller wavelength. Why are we using 193 nanometers? And that's a good question. We'll discuss it in a moment. But actually nowadays, currently we're starting to use extreme ultraviolet, or EUV light, which is 13 nanometers. So 13 nanometers actually alleviates many of the problems that we've been dealing with for the last several years. But as I said, we've been using this 193 nanometer light a laser for the last 20 years or so, I think, something like that, and it's down to 7 nanometer technology, and we've been making it with this with that wavelength. Okay, so just a couple more things about photolithography. First of all, we use something called a step and scan method. So the lens, okay, this thing is huge. We'll see a picture of it on the next slide, and we can't really move it because it's really big. On the other hand, the wafer is not so big. It's down here. So it sits on a machine called a stepper. And the stepper moves in both directions, this way and that way. And so what we're actually doing is we're taking the wafer, sticking it under the focal point of the laser that goes through the mask, and we're moving it around. The mask itself, first of all, is made to be 4 times as large as the image that's made underneath it, but also it doesn't cover the whole wafer, so there are many steps of the mask over the wafer. So we have to go in and develop this area, then develop this area, then develop this area, and that's done by moving the wafer underneath, and as well as the light. The light will also move in a certain way. That means that there are different orientations of the transistors that will be different at very small dimensions. Another thing is what we call optical proximity corrections. So if we take something that we drew like this, is some nice, straight lines here that are very right angles and so forth. When we go and we make these, if we look at it, what we get are these really ugly features. And these are old technologies where it was actually pretty good shape. This still is the same as that, but in newer technologies, we get just a blob that has nothing to do with what we actually wanted to do. So when we send our mask set out for fabrication, what is done is that we run these optical proximity corrections on the mask, and they find out how the light's going to actually refract, and and if they should add all kinds of little features, like as you can see here, these little handles are added, and when you shine the light through that, you get something that's much more close to what we actually intended at the beginning. So this is something that's done after we tape out our chip, before the masks are made. Okay. Another thing that I wanted to mention are phase shift masks. So as you know, when we shine light is a wave, and when we shine it through these little slats, what we're going to get is we're going to get refraction. So we're going to have all of these waves that are not very, this is what we wanted to get, right? But we're going to get these sine waves, and they're going to overlap with each other, and we're going to have these things that come out, and it's going to make a mess. In fact, we're not going to get any resolution at all. But instead of that, we can do some cool tricks. Like, for instance, we can change the phase of adjacent slats here, and what we get is, instead of this this merging of the two waves, we get actually the waves that negate each other. And doing this, we can get really nice resolutions. So that's another trick that's done a lot using phase shift masks. And finally, as we mentioned before, multiple etches, but there's also multiple exposures. So, for example, let's say we have a we can create features that are 90 nanometers apart. So we'll create two lines that are 90 nanometers apart. And then with another mask, we'll make another two lines that are 90 nanometers apart. And let's say that that's what we can do. Well, if we do it with in two steps, but we shift this this mask 45 nanometers from the first one, then what we'll get is, if this is made in the same place as this, our feature size will be 45 nanometers. That's called double exposure, okay? And in 7 nanometers, they do something like quadruple exposure. So they'll do 4 of these types of exposures. It takes 4 masks to make 1 metal layer because of that. So that's one of the things that we could do to really get down to these really small sizes that we're developing today. So here's a laser stepper. You see that this is the lens. It's really big. Here's where the wafer sits and moves around. Okay, this is making the laser and sending it through. That's a big machine. That's why you can see that this thing doesn't move around. These are often made by this company ASML, a Dutch company that makes these, and they also have the breakthrough with the EUV stuff that's coming out nowadays. So if we look at a map of a graph of lithography scaling, we see that a long time ago, when we were at 6 microns over when they made the Intel 4004, well, we had these big lasers that were 400, 440 nanometer wavelengths. And every once in a while, the wavelength of the laser was lowered, okay, but sometime in the mid 2000s or so, they reached this 193 nanometer laser, and maybe moved over here, as you can see, to wet. It was probably expected that this was going to go down to something else, but in fact, what was pretty common sense was that we were going to change to this EUV, which is 13.5 nanometers. Now, that's a big step. Why wasn't it done? So that's a good question, but it turns out that 13.5 nanometer wavelength is really problematic. First of all, you have to make it in a vacuum, which is one thing that, let's say, can be dealt with. But the bigger problem is that that our quartz glass is opaque at that wavelength. So in other words, when we would try to make a photo mask and shoot our light through it, it would just bounce off it. So we can't do that, and it took many years, I would say 20 years of development or so, until just recently we've been able to fabricate masks that actually can, or a photolithographic methodology that can actually develop in in extreme ultraviolet. And the way it's done is by bouncing the light waves off of a set of mirrors. It's kind of crazy to think that they did this, but after a lot of research, now these are the machines that are being made and being used by TSMC and by Samsung and by others to make the very advanced nodes such as the 7 Plus and 5 nanometers. Okay, another point about transistor fabrication is tip extension. So, for various reasons that we'll be discussing later on in the course, we need something called a lightly doped drain, or an LDD. That means we need the diffusion, the drain and the source that are close to the channel to be lightly doped, rather than the strong, the N plus or whatever, the strong doping we have there. However, we can't make the whole diffusion lightly doped, because in order to make the contact good between the contact and the diffusion, and so we won't have high resistance between the contact itself and until it reaches the channel and the source and the drain, we need a heavily doped drain, so it'll be close to a conductor and not a semiconductor. Okay, so what we do is we use what's called a tip or a spacer. So let's see how this is formed, and then we'll understand what it is. So we do our photolithography. Now we cover up these foxes over here, and we shoot our ions at a little bit of an angle, and this angle helps us because it actually makes the source and drain actually go a bit underneath the channel, and we can get a smaller L effective than the L drawn. This would be the L drawn, the length that we drew. And at least until some pretty deeply nanoscaled technologies, we'd always get a smaller length than we actually would draw. And that was one reason, because we were able to shoot these ions actually underneath the gate. Okay. Then we're going to build up an oxide layer on top of everything. So as you see, something interesting in the oxide layer, here it's flat, but here we have this gate, and the gate's pretty high actually. So what happens is when we deposit this oxide, it actually is pretty thick over here, much thicker than over here. Okay, and therefore if I etch it now, and I etch it away at a constant rate, and I just want to etch it away until I touch the surface of the silicon, what happens is I etched away everything that was over here, but here I didn't etch away all that much, and therefore this excess oxide is left here on the sides. Okay, then if I'm going to make my so the first implant was a light implant. That was an N implant, not an N plus. Now I can implant this N plus, and what happens is that these guys over here, they actually guard what's underneath. So the dopants that come in here, they don't get stuck under here, but the dopants that come over here do get stuck under here. So here we have an N, and here we have N plus, and that created this lightly doped drain. It also left this spacer thing here that you can see in the pictures over here. You have these spacers or tips that are on the sides of the gate. Okay, so those were the things I wanted to discuss in the stage of transistor fabrication, and now we're going into the back end. The back end are all the metal layers that connect between the different terminals of the transistors and so forth. Okay, so the first thing is contacts. So contacts and vias, those are the little tunnels that go up between layers. Contacts are the ones on the bottom level that touch the diffusions or touch the gates. Above that, we call it vias. So from metal 1 to metal 2, we call it via 1. From metal 2 to metal 3, we call it via 2, etc. And we use what's called the Damascene process. Damascene comes from the word Damascus, and it's a type of art that was developed, I guess, in Damascus. And it's this type of art. So if you see these types of like plates that have this type of interesting style, and we'll see how it's made in a second, which is the same way that we make the contacts. Okay, so we start with our substrate over here that we have after we've made our spacers and everything. We have our LDDs. We have everything going on here, and now we build this big oxide. And something I haven't mentioned up till now, which is done at almost every stage except for maybe making the spacers where we don't want to do it, is that when we finish a stage, what we do is we polish down our the last layer that was made. We polished using using a process called chemical mechanical polishing, CMP. Okay, it's both abrasive, mechanical, and chemical. We stick some chemicals in there to do it really well, and it polishes really well and really finely. This is called planarization, and we do that after every stage, so we can start at a very planarized area, so everything is exactly the same and equivalent across the whole thing. So after planarizing, what we do is we use photolithography, mark off the areas we don't want, and then we mark off the areas we want these contacts, and we etch them away. So we probably bombard it with some ions that eat away the oxide until we touch the bottom, which is over here, it's the polysilicon or the metal gate, and over here it would be the diffusions. Okay, so we have this hole now in our structure, and what we do now, and this is what's done in Damascene. One more point. We put something called a liner in. So this is a material. Usually we use titanium to do it. It's a material that that makes sure that it connects really well to the sides, and it's also adhesive. So that's a liner material. And as you see, we pour it over the whole wafer. one thing I want to point out is, so we want to have a tunnel over here. We do not want to have this thing shorted to the sides, and right now we created this short, but we'll get rid of it in a second. Okay, the next thing we're going to do is we're going to pour our plug into there. Our plug is the material that we're going to make our contact out of, and it's usually tungsten. Okay, so we pour our plug into these things, but we pour much more. We do this excess thing, so we go way over. So we make sure that everything is flooded basically with our plug material. And now what we do, and this is the Damascene process, we filled everything, we covered everything with our fillet. Now we etch away until nothing is left. And as you see, when we etched all the way until we touched the oxide again. Now why is this done? Because that way we removed this excess liner that was going to short our contact over here to somebody that he didn't want to be part of. And what we got left is just this liner filled up with this plug. And that's exactly the contact that we wanted. So if we look at some pictures of it, you see this nice contacts over here, either to a diffusion or a poly. They're both called contacts. In newer processes, actually we get different names for the two different types of plugs, just because processes get more complex and now they have to take care of them separately. Here you see again, the contacts are huge. This is from in 28 nanometers from the Apple A7 chip. And you see that the contacts are really huge. One of the things you have to realize about this is that these contacts are actually going to have a lot of coupling capacitance and so forth. But they're really big, okay? So those are the contacts that they're making nowadays. I just want to point out some things that that affect our design rules. So there are misalignment problems that can happen in contacts. So what we want to do here is to make a contact to a diffusion. So we have our N plus diffusion over here. We have our metal that's running up here, and we want to connect the two through this contact, right? This is the contact layer. But the problem is that this is really small. And again, it's made with several, okay, we first made this bottom layer, and now we're going to make the top layer, which is the contact, right? Very easily we could have some misalignment, just a small thing, a few nanometers between the two process steps. And if we had it, that's really bad, because then we're going to pour our metal into this area. And remember, this is the channel. Okay, it could even be a different transistor, but this is the channel itself, and we just shorted the channel, and that's not what we wanted to do. Okay, so this is really not the thing that we wanted to do. So what do we do to take care of this? We ensure that we have overlaps. So in our DRC rules, for every contact or via that we're going to have an overlap of the layer underneath and the layer above it, and that's so in case we have some misalignment problems, it won't cause something that's going to damage our chip. Okay, I just mentioned before planarization with the chemical mechanical polishing, or CMP process. So here you can see a picture of the CMP process, and you see that this big wheel here turns around with both the abrasive material and some fluid on it, and that's how it planarizes the wafer, and it makes it really shiny and nice and mirror-like. Does it really well and perfect. Okay. So we have our contacts, we learned about our planarization, and now we'll just discuss the back-end layers, or the metal layers. So as you can see here, these are stacks. What we have here is we start with the silicon, we go in a contact, the tungsten plug up the silicon, then we start with metal 1, we have a via, a metal 2, a via, a metal 3, a via, and so forth. Finally, at the top we have this passivation, which is some material that protects the chip from mechanical damage. Okay, and we can see here, so we have these metals, we have the vias, as I said. The first layer is called a contact, as you can see here. The second layer would be between metal 1 and 2 is called via 1, then via 2, via 3, etc. The white areas, okay, that is silicon dioxide or some other material that is an interlayer dielectric. Okay, in fact, it used to be silicon dioxide, since we don't want all kinds of coupling capacitances in general between top and bottom, between the contacts, or internally in these metals between their pieces, like between this guy and this guy. What we do is we actually change the material here, so instead of being a silicon dioxide, nowadays it's a low-K material. We'll discuss that in a later lecture. Okay, so for a long time, we were using aluminum wires, but aluminum isn't a very good resistive wire, and also can get hurt by electromigration, as we'll discuss later. So it was something that was always wanted to do was to use copper interconnect. And there's a problem because copper has a chemical reaction with silicon, and so it will diffuse into the silicon, and then it'll cause shorts, and it doesn't work well. So you cannot put copper directly onto the silicon dioxide. Okay, it took a long time to solve this, and finally the IBM, along with a guy I know, Professor Yossi Shacham, who was at Cornell at the time, they developed this dual Damascene process, which solved the problem and is now used by everybody. And we're only basically using copper interconnects for most of the layers. Okay, so this is our substrate, our transistors and so forth. What we're going to do now is do something similar to what we did with the contacts, but again, now it is dual Damascene, and this is going to help us protect our copper from going into the silicon dioxide. So again, we're going to fill up our whole thing with all this big silicon dioxide, and we're going to etch it away. Okay, and after we etch it, we're going to leave room for the contacts as we did before. Okay, now again, what are we going to do? Aha, one more step. We're going to now etch away the metal. So this is our contact layer. This is already our metal 1. So we already etch away with a separate photolithographic process our metal 1. We haven't stuck in our liner yet, and we haven't filled our plugs yet. Now we are going to fill it with our liner. So the liner is going to both line the contacts, but it's also going to line the metal 1 areas. And this is very important because this liner is going to protect the, this is going to be from a material that is not going to diffuse into the oxide, into the silicon dioxide, or into the interlayer dielectric, and it's going to protect. So it's going to protect the metal, the copper metal, okay, from diffusing. Now we're going to fill up with our plug material and then our metal material, which is going to be copper. Okay, so this area is going to be the plug material, which is tungsten, and then this area is going to be our copper layer. Okay, and again, we're going to way overfill, and then we're just going to etch down. So this was a dual Damascene process because in one step, basically, we filled up both the contacts and the metal before we etched away. We're also going to cover with liner so it doesn't diffuse into the next layer of silicon dioxide. So as a summary for what we did and discussed, we discussed lithography, we discussed oxidation, that was building our oxides, we discussed etching, that was cutting away our different materials, ion implantation, that was shooting our dopants into the silicon, epitaxial growth we didn't actually discuss, but that's growing layers of like silicon above other layers, not from the substrate itself. Chemical mechanical polishing, deposition, that's putting down all kinds of materials. Diffusion that is caused by annealing, like rapid thermal annealing. Metal plating, that's depositing the metals and so forth. And you see the different steps here and the temperatures that they're run at. And this is something we have to pay attention to. And we can't do everything, any step before any other step, because we have to make sure that we don't ruin the other steps, the previous steps, for example, because of the temperatures that we have there. So that was it for our detailed process flow, and in our next section we'll discuss process variations.